Okay, so some more logarithms. Right, so calculating these things. So in a certain sense, well, they're difficult anyway because they're defined as inverses. And so what we're going to do is we're going to kind of find out what they are. Well, I'm going to show a few ways of doing, two ways I think in most cases, by basically turning them into an exponential equation. Okay, so I'm going to do that for all of these first. And when you get the exponential equation, it's still not an easy problem. And to solve that problem, you actually need to go back, turn into a log, and use a calculator. But we want to be able to work with things. So what we're going to do is set these up. We're going to say let this equal to x. Okay, and this, if we do this, we can at least turn it into a problem that's a bit more familiar to us. Now what I'm going to do here is I'm going to look at this as an equation. Now you don't, this is highly what I recommend, think of it as an equation, but if you want, you can just rewrite it using this formula, but I'm not going to do that because I spend enough time talking about functions and stuff. So I'm now normally, like, you're looking for x here. Yeah, so actually I have to go back on what I said. Actually, I do have to use this, sorry. So we're going to rewrite here, look, log base of a number equal to power can be rewritten as base to the power equal to the number. So this can be written as base, which is 2, to the power equal to the number. And the question becomes 2 to the power of what gives you 8. Now to solve that, you need to go at logs. But we'll just do this in our head up to a degree. So what number? So 2 by 2 is 4. 2 by 2 by 2 gives us 8. So therefore x, in other words, log base 2 of 8 is equal to 3. We did that in our head, not necessarily very ideal. There's an alternative way, which would be to use basically this. So basically this would be, if you've got log base b, b to the p, b to the power and log base b are inverses. So start with p, then get b to the power p, and then do basically log base b gets rid of the b to the power, you're left with p. So one way would be to write the number in here, so the 8 as a power of 2. So that's another way of doing this. If you did that, you'd get log base 2 of 8 is equal to log base 2, and try and write the 8 as a power of 2. You get 2 cubed, and then use the fact that 2 to the power and log base 2 are inverses, and so log base 2 gets rid of the 2 to the power, and you're just left with 3, similarly. Okay. I think we'll keep doing it both ways. So let this thing here equal to x. Then use this thing on page 165. So log base power equal to number implies base to the power equal to number. Now you'll have to practice doing this. You won't learn it watching me. So base to the power 3 to the x is equal to the number 81. And then you just think in your head. And this is how I used to actually teach logs, not as inverses, but saying log base 3 of 81 is the question 3 to the power of what gives me 81, which is essentially what's written there. And then you just play around. 3 by 3 is 9, 3 by 3 by 3 is 27, 3 by 3 by 3 by 3 is 81. So x equal to 4, in other words, log base 3 of 81 is equal to 4. Alternatively, we can write log base 3 of 81 and think about 81 as a power of 3. So I hear it interesting ways. It's 9 by 9, and then 9 is 3 by 3, and the other 9 is 3 by 3, so it's 3 to the power of 4. And then 3 to the power and log base 3 are inverses, so log base 3 undoes 3 to the power, and you're just left with 4. Similar story. Okay, and next one, which is a bit harder. And when these get hard, that is when you would use the calculator. I recommend you get a calculator with this variable base. If you don't, things are a little bit difficult. You should get a calculator with one of these variable bases. So log base 25 of 5 half. Now let's see where that half comes from. Yeah, it's not easy. There's no two ways about it. Let's see how we get on. We might be able to solve it some weird way, I think. Yeah, I'm going to solve it a weird way. because the way some of us can do this in our head, but not everyone will be able to do it in their head. So log base of power equal the number, base of the power equal to the number. So what I'm going to do this a slightly different way here. I'm like, what? You know, now it's definitely not 1/5, because remember, the power of 1/5 means the fifth root. It's not that. So one way you could do this is actually turn it into an exponential equation, because if we look back, if you have two equal powers, essentially you can get rid of them. So if I can do something like this, so what I could do is get them both in base 5. So 25 is 5 by 5 is 5 squared, and 5 is 5 to the 1. And then here what you can do is you're thinking of, I'm applying log base 5 both sides, or whatever. Well, there's probably an extra line I need to do here. Repeated powers means multiply the powers. So you are allowed to say 2x equal 1. Why? Because 5 to the power is invertible. Its inverse is log base 5. So this is weird. We've done some messing around, and now we've got an equation, and now we're going back into the log place to solve it. So log base 5 gets rid of both the 5 to the power, so you get 2x is equal to 1. And then how do you get rid of the multiplied by 2? You do divide by 2 both sides. Well, divide by 2 gets rid of multiply by 2. If you've got an equation, apply divide by 2 to both sides, you get another true equation. So the divide by 2 gets rid of the multiply by 2, and 1 divided by 2 is a half. So how do people do that in their head? Well, they think something like this. Log base 25 of 5, and they recognize that 5 is the square root of 25, and then they recognize that the square root is to the power of a half. Running out of space here. And then log base 25 and 25 to the power inverses, you're just left with a half. Okay, similar story here. Let's see what happens. Can I write this as a power of 2? We'll do like this one. So you can do something similar here. Realistically, I would expect 80% or not more of the class to actually use the calculator. If you had to calculate, you'd have to use a calculator, but let's see what we can do. So log base 2, 0.125, do you recognize that as anything? I appreciate it's ridiculous using the calculator, we can just bang the whole thing in. It's 1/8. And what is 8 in relation to 2? It's 2 by 2 by 2. 2 cubed. And then what is division by 2 is negative powers. And then 2 to the power log base 2 are inverses, so the log base 2 gets rid of the 2 to the power, and you're just left with -3. Okay. So this is kind of working with logs. Another one here, this one looks a good bit harder actually. Not really sure how, yeah, so this one is probably, so people who do this in their head, some people will, I'd say maybe 3 or 4 people in the class can do this in their head. The rest of us, what we might do is we might solve it equal to x and then try something else. Okay, so we'll use this thing here. So if you've got log base power, log base number power, log base number power, you can turn it to base to the power equal to number. Now, one thing I'm not going to spend a lot of time on is like you have to be, I can't teach you this pattern spot, like what's the A, what's the Y, what's the X. You have to look at this and see that for yourself. For me, it's base number power. So base to the power is equal to the number. That's what I see, but you might see it slightly differently. So what are we saying? Base to the power is equal to the number. Now what we could do here is, if we could turn it again into an exponential equation. Now the problem is we haven't got like powers. Like if we look at that thing I was looking at, the bases have to be the same. So these are different bases, that's an issue. So, but what I could do is I can write them both as powers of 2. So I can write the 8 as 2 by 2 by 2, 2 cubed. And I can write the 4 as 2 by 2. And then I can do repeated powers means multiply the powers. And now look where I am. And I can do, to get rid of 2 to the power, I can apply log base 2, which is different actually, isn't it? Because that was funny, because I had log base 25, and then I ended up using log base 5. Similar story here. Now this is the justification. Like I'm quite happy for you just to write down 3x equal to 2. That's okay. So you get 3x equal to 2. And then the thing I'm looking for, which is log base 8 of 4. Remember, this x is what I'm looking for. Well, I've introduced x. So this is the power of algebra. Like, it's hard to actually do this without the x. You have to do it in your head, which is more difficult. But anyway, x is multiplied by 3. I don't want it to be multiplied by 3. I want it to be on its own. So I apply the inverse of multiplying by 3, which is dividing by 3. You get rid of them and do it to both sides. If two things are equal, apply the same function to both be equal. So I end up with x is equal to 2/3. So some people may or may not be able to see that if you take 8, okay, do the cube root. This is how people who do it in their head do it. That's 2. And then square it, you get 4. And so this weird thing here, which is equal to 4, so it's 8 to the power of a third squared, and a third read power multiplied by 8 to the power of 2 over 3. So the 4 is 8 to the power of 2 over 3, and so log base 8 and the 8 to the power can do each other, and you're just left with 2/3. Okay, so this is the kind of question that we'll want you to attack here. Right. Now remember, from algebra, when we're looking at equations, this idea of the onion, work from the outside. So the thing kind of on the outside to get at, you're looking for x, sure, but this plus 8, you want to get rid of that. So what's the inverse of adding 8? Well, it's subtracting 8. If you subtract 8, that 8 will be gone. Now if two things are equal and you apply the same function to both of them, equal inputs, equal outputs. So do the minus 8 function to both sides, you get 2 to the power of 5x is equal to 8. Now what you can do is you can go down the line of writing them both as powers of 2, but I'm recommending you want to get that x on its own. Look at this 2 to the power function. What is the inverse of 2 to the power? Log base 2. And we're going to be using the calculator after this. So do log base 2 to both sides. It's the inverse of 2 to the power, so it'll get rid of the 2 to the power. I'll just have 5x equal to log base 2 of 8. And like in an exam situation now, you can use your calculator here, and that's just going to be equal to 3. Okay. Maybe I'll do that in brackets. Yeah, just use your calculator, no bother. Now we didn't before because we wanted to understand how logs works. So 5x equal to 3. X is multiplied by 5. I do not want to multiply by, I want it on its own. So the inverse of multiplying by 5 is divided by 5. I can do this divided by 5, but really I want the 3 divided by 5. Done. Working from the outside. Trying to make it simpler by applying inverse functions. So here the plus 8 was in the way, apply the inverse to both sides. Then the 2 to the power was in the way, apply the inverse to both sides. Then the multiplied by 5 was in the way, apply the inverse to both sides. Big idea. This is how equations you want to think of them. Okay. Now we've got this e here. Now e is actually a specific number. We'll learn about it a little bit later. It's a specific number. It's like pi in that its decimal expansion goes on forever and ever, but that's how it starts. But we'll just note on the calculator, log base e is ln of x. So you see it there, ln is the same thing. So if I do ln of 5, 1.609, work whatever I'm doing. Log base plus 5 was 1.609. Yeah, same thing. Okay. So if you want log base e of 18, you do ln of 18. So you don't have to input this because it's a pain to input the e. So if you need to input e, it's probably the easiest way is e to the power 1. But some things have it like here, it's on the red, it's like a shift. Same number, okay. Or some kind of shift. The shift would be harder. So back to the question. Now the first thing is what I call bema. You've got the exponential happens before the multiplication. So in terms of the onion peels, the 5 is on the outside. You don't want that 5 there. You don't want that multiplied by 5. What's the inverse of multiplying by 5? Dividing by 5. do it to both sides, it'll get rid of the multiply by 5 and you'll just have e to the 3x. And 90 divided by 5, I can go into the calculator if I want, is 18. Now I've got the e to the power function. Now I'm going to just write something down here. So the inverse of e to the power, remember the inverse of, say, all these exponential functions is the log base e, and that's the same as ln. Now, so the inverse of e to the power is log base e, and ln is just a shorthand, log natural. So the inverse of e to the power is ln. So I'm going to apply that function to both sides, and so I end up with 3x is equal to ln of 18. Now I have a choice here with ln of 18, and it depends kind of how you think. So for me, this is a perfectly good number, and I'll work with it. I'll show you the alternative over here. And then what I do then is, I want to get x on its own. It's multiplied by 3. So to get rid of the multiply by 3, I must divide by 3. And I'll do that to both sides. So my answer is x is equal to log 18 divided by 3. Now the 3 can't get at the 18 or anything like that. Now what I might do at this stage, if I want to get a feeling for the answer, is to do a rounding. Now anything you put into the calculator, because the ln's all go on forever and ever and ever and ever. Like it's more digits than that, it goes on forever. Basically all of them. And so what I might do is I might do rounding. Now one thing I'm going to talk about will be significant figures and decimal places. I'm assuming you know what decimal places are, and in the assessment I might do that, but I will advise you from now on, maybe not in this module, but after that, to use significant figures. So it just means non-zero numbers, and to use 4 significant figures. I won't make the argument here because it doesn't quite belong, but I'll just say what significant figures is. So that's not significant, it's a 0, 4, 9, 1, 2, 3, 4. And you round it if you have to. So I'll round it up, 9635. So approximately, so this is a perfectly good answer for me. It's approximately 9635. Now the alternative I was talking about is you mightn't like this ln of 18 here. So you might want to put it into the calculator early. Now the issue is, when you round, like there's a difference between these, and when you apply functions to these, the difference between them grows bigger. So for example, like say if I took log 18 over 3 and say applied the to the power of 5 function. Now if these were equal, if I did them both to the power of 5 and looked at the difference would be 0. But in fact here it isn't. Okay, so the issue is, if you round early, you're going to apply more functions, and the difference between them can get bigger. So you have to be a little bit careful. But I won't be too worried either. So the equals is not quite correct for what I'm going to do, but I'll do a decimal approximation, 2.890. And then I would divide both sides by 3, and you see I'm dividing not log of 18 but 2.890, which is only an approximation. And I get, and lo and behold, you get what's called a rounding error. There is a difference between these. So the rounding is dangerous, and when you apply more functions, that difference can get bigger. It's not something to be terrified about, but it's something to be aware of. We're probably not going to dock marks for a mistake like this, but I mean, which one is better though? Okay, so I got some properties of logs. Now these would have been very important before, but this is kind of something we've caught a little bit, but they still might come up, so we still need to see them. So you define what a logarithm is. It's the inverse of an exponential / power function. You must investigate common properties. What happens if you take log of a product, things multiply together, log of x by y, log of x over y, what about log of x to the n? I will say that these properties are here. Where are they? Here. I'll call them log props. I'll call them props. There, so you don't have to learn them. We might just show where they come from. So basically, see the addition here. Remember, logs are powers. So you got a sum of powers. Look where it comes from. a difference, so it comes from here, and a multiplication is coming from here. So they're coming, these are related. So this section, as I said, it's not too important, so I'm going to go pretty quickly on it, I think. Okay, so what is log of 8 by 16 to the base 2? What am I going to do here? So let's turn this into base to the power. So yeah, so I'm not going to put much emphasis on this. I'm going to go quite quickly over the next bit. These things are out there. Right. I definitely need this one. That one's definitely important. Okay, let's go. I'm going to go relatively quick now. If you want to listen, pause and re-listen. So I'm going to use this thing here to rewrite this log base of a number equal to the power. Rewrite it as base to the power is equal to the number. Then I'm going to note that 8 is 2 to the power of 3 and 16 is 2 to the power of 4. I'm going to note that like powers, you add the powers. And I'm going to note also that log base 2 of 8 is equal to log base 2 of 2 cubed. Log base 2 and 2 to the power are inverses, so this is equal to 3. And similar story, log base 2 of 16 is equal to 4. I'm going to apply to both sides of this, because it is an equation, log base 2 to get rid of those 2 to the powers. I could arguably say that I get from here to here by applying the 2 to the power function. I think I will say that. So if I do 2 to the power of log base 2, I get the 8 by 16. So I've written, they've kind of gone, that's gone there, and that's gone there. And now I'm undoing it, and I get x, which remember is log base 2 of 8 by 16, is equal to, now the log base 2 will get rid of this 2 to the power of 3 plus 4, and 3 plus 4 is log base 2 of 8 plus log base 2 of 16. Now there's nothing special here. There's probably a bit of messing around that made it nice that 8 and 16 were perfect powers of 2, but actually you don't need them. We've got a general rule. Log any base of x times y, logs turn the multiplication into addition. And that's in your log properties in your tables. So evaluating this thing here, the logs, now this is working the other way around, and this is a bit harder. So I've said it turns multiplication to addition, that's nice, but the equals works both ways. So if I've got a sum of logs, it's a log of the two things multiplied together. Now you have to be able to see that pattern yourself, and it's not going to be a massive deal in this, so I'm going to go quick. Two by 32 is 64, and 64, 4 by 4 is 16, by 4 again is 64. So what I did there was 4 to the power of 3, and 4 to the power of log base 4 inverses. So this thing all in all is equal to 3. What about this thing? So this is, I'm gonna cheat here actually. So this is equal to log base 2 of 8. I won't say where I've cheated here. So if you've got multiplication, logs turn multiplication into addition. So we got log base 2 of 8 plus log base 2 of 8 plus log base 2 of 8 plus log base 2 of 8, and that's 4 by log base 2 of 8. And look what happened, the power 4 turned into multiplied by 4. So again, nothing special here. Log base b of, I think I'll call it a to the n is equal to n times log base b of a. So logs turn powers into multiplication. So again, I'm going quite quick, it's not too important for me. So this 25 to the 60 is a very big number. Can this handle it? If I go a bit bigger, so if I say 600, calculator can't handle it. I wonder, can it even handle the log base 5? 25 to the 600. can't handle it, but we can, because we know that logs turn power 600 into multiplied by 600. And we know that log base 5 and 5 to the power inverse. So if I can write 25 as 5 to the power of something, then I'm done. Yeah, sure enough. Log base 5, 5 to the power inverses. So I get 600, and this thing is just equal to 2. So 600 by 2 is 1200. Calculator couldn't do that. We could, which is great. And then the last one, I'm going to go quick enough again, I think. I'm going to cheat again. I won't explain where I'm cheating, but I am. So this is log base 3 of 9 by, divided by 27 is 27 to the power of minus 1. Logs turn multiplication into addition. And then logs turn powers into multiplication. So instead of to the power of minus 1, it's multiplied by minus 1, which gives you a subtraction. So what you have is another general thing. Log base b, any base of a over b, is equal to log base a minus log base, oh crap, terrible use of symbols, sorry. So let's make this a c. Yeah. Again, all these properties are given here. Log turning multiplication into addition, division into subtraction, and powers into multiplication. As I said, I am going very fast here because it's not a massive deal for this. So the log turns, a subtraction came from a division. 80 divided by 5 is 16. 16 is 2 to the power of 4, and 2 to the power, and logs are inverses. So log base 2 gets rid of the 2 to the power, you just get 4. Okay, and we'll talk about these laws a little bit more in the next lecture.